Welcome. In our first module, we're going to review equations and inequalities. So we'll focus on a few important examples that are somehow fundamental to studying mathematics. So we will focus on the examples of lower order polynomials, by which we mean things like linear polynomials and quadratic or second order polynomials. So the key thing to understand about what makes a polynomial complicated or not is what is the largest power of x involved. So here we have a power of x at most 1. So this is called first order. So I have something like ax plus b equals 0. So you might be familiar with these as equations for lines. So very simple polynomials compared to what we could have. We will also look at a slightly more complicated example of second order polynomials. So we say that this is second order because there is a 2 in the exponent right here. So this is the term that really makes it complicated, this ax squared. Right? So keep in mind that a, b, and c are what are called coefficients. And they will typically be defined for a particular problem. And they're not what makes it complicated. It's the powers of x that make things somehow complicated for us. Right? So we will develop something called the quadratic formula for working with second order polynomials that I like to abbreviate as QF. Once we've finished with quadratics, we'll look at another class of functions and the equations corresponding to them. And this is the exponential and logarithmic functions. Okay, so exponential functions look like y equals a to the x, where a is a fixed base. So you can think of a is constant here, and x is the variable. So exponential functions on the face of it look a little bit like polynomials, but they are actually quite different. So an exponential function could be something like 2 to the x, 3 to the x, something called e to the x is another famous example, versus polynomials don't have the variable in the exponent. These are things like x cubed, x squared, x to the 100. So they actually look quite different and have very different behaviors. We will also discuss logarithms, which are somehow inverse to exponentials. So what does it mean to say that y is equal to the logarithm base a of x? This is just a compact way of saying that if I take a number a and raise it to the yth power, I get x. So in a very concrete sense, logarithms and exponentials are inverses. So commonly logarithms are used as a tool. Right? They're used as tools to solve exponential equations. And then finally, we will study the absolute value. Okay, this sometimes seems complicated and challenging, but actually I think has a very simple formula. It just says whatever your input is, if it's positive, leave it alone. If it's negative, drop that negative sign. So the absolute value of a would be equal to a for a greater than or equal to 0 and minus a for a less than 0. So as an example, the absolute value of minus 2 is 2, and the absolute value of 2 is 2. So absolute value says if there's a minus sign, kill it off. If there's no minus sign, don't do anything to it. So we will discuss both equations and inequalities. Now, in many ways, they're solved the same way. In fact, what we'll do is for inequalities is essentially solve an equation first, and then make some slight modifications at the end to address the fact that we actually have an inequality versus an equation. Okay? So just to be totally clear, what do we mean by equation? We mean something like f of x equals, say, a constant a. What do we mean by an inequality? We mean something like a function f of x is less than or equal to some constant a, or greater than or equal to. So how do these solution sets differ? That is, if I give you something like f of x equals a, what would you expect to get as a solution? Well, you would expect something like a discrete set of points. So finitely many points are typically solutions to equations. So for example, let's be real simple and say that f of x is equal to x plus 1. And I want to solve the equation f of x equals 0. Well, okay, I can do this with some nice algebraic manipulations. I can say x plus 1 is equal to 0, which means that x is equal to minus 1. And the point I want to illustrate here is that this equation had a single point as a solution. In distinction, inequalities typically have regions as solutions. So instead of having one particular or a finite set of particular solutions, I get infinitely many solutions corresponding to all the points in some region. So let's look at a related example. Let's say I had f of x was again equal to x plus 1, and I wanted to solve the equation f of x less than or equal to 0. Well, I solve it in much the same way. I would say this means x plus 1 should be less than 0, so x ought to be less than or equal to minus 1. So now I don't get a single point, I get infinitely many points. Minus 1 will work, so will minus 2, so will minus 3, and so on. So this is very different structurally. Equations typically have a discrete set of points as solutions. Inequalities typically have infinitely many points as solutions, and they correspond to a region of the real line, for example. Now, in this case, it was quite easy to just sort of add and subtract minus 1 to both sides to solve them, these equations and inequalities. Sometimes you'll be encountering equations that are not so obvious, where specific formula can be very helpful for us. So we'll focus next on what's called the quadratic formula, which is specifically designed to handle second-order polynomials, which are pretty tricky without it.